The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so today's lecture, right, is relevant for a couple of reasons, right? We're going to be talking about probabilistic planning later, right? And in these cases where you're doing planning in large state spaces, right, is very difficult. And one of the main things you can do, it could be MDP planning, it can be, strip style activity planning or the likes, but you have to be able to figure out how to deal with those state spaces. So Monte Carlo Tree searches is one of the techniques that people kind of identified over the last 5 years as having an amazing performance improvement over other kinds of sampling-based approaches. So MCT is very interesting from that standpoint. And then if we link it to the last lecture, right, then the combination of something which is trying to learn about each kind of policy, combining it with search, is very powerful in this case due to the state-of-the-art techniques for that is Monte Carlo Tree search together with a modulator neural network. Okay.
Good morning, everyone. As Professor Williams just said, we are going to be talking about Monte Carlo Tree search today. My name is Ian, and I'll be leading the introduction and the motivation of this presentation. By the end of this presentation, you will know not only why we care about Monte Carlo tree searches. As Professor Williams said, there's so many algorithms out there. Why do we care about this specific one? And second, we'll be going through the pros and cons of MCTS as well as the algorithm itself. And then lastly, we will have a pretty cool demo on how it's applied to Super Mario Brothers and the latest AlphaGo AI that built the second best leading Go player in the world. So the outline for today's presentation is first we're going to talk about pre-MCTS algorithms, the other algorithms that currently exist out there, and just a few of them to lead into why we do care about MCTS and why these other algorithms fail. And second, we'll talk about Monte Carlo tree search itself with Yo. And lastly, Nick will tell you more about the applications of Monte Carlo tree search. So the motivation of these kinds of algorithms is we want to be able to play games, and we want to be able to create programs to play these games, but we want to play them optimally. We want to be able to win, but we also want to be able to do this in a reasonable amount of time. So these three constraints itself lead to different kinds of algorithms and different algorithms with different complexities and times to search. And so that's why today we're going to be talking about Monte Carlo tree search. And you'll figure out in a few slides why we do care. So these are the types of games we have. You have this chart where there's fully observable games, partially observable games, deterministic, and games with chance. And so today, the games that we care about are the games that are fully observable and deterministic. And these games include games like chess and checkers and Go. And we'll also be talking about another example with tic-tac-toe. So these pre-MCTS algorithms include deterministic, fully observable games, like we said earlier. And the idea of this and the nice thing about these games is that they have perfect information, and that you have all of the states that you need, and there's no opportunity for chance. And so the idea is that we can construct a tree that contains all possible outcomes because everything is fully determined. And so one of these algorithms to address this is the algorithm Minimax, which you might have heard before. And the idea of Minimax is to minimize the maximum possible loss. Now it sounds a little weird in the beginning, but if you take a look at this tree, this red dot, for example, is the computer. And so in the computer's eyes, it wants to beat its opponent, and we're assuming the opponent wants to win also. So they're playing their best game as well. And so the computer wants to maximize his or her points, but also knowing that the opponent or the human wants to maximize their own win as well. And so in the computer's eyes, it wants to minimize the maximum possible loss. Does that make sense to everyone? Yes? Okay. And so in the example of Minimax, we're going to start with a a tic-tac-toe board, where the computer is this board right here, and the blue tic-tac-toe boards are the states that the computer finally chooses. And it's anticipating what the moves the human could play. So if you take a look up here, So if you take a look up here, here's the current state of the board. Okay. Current state of the board, and the possible options for the human are this guy, and no possible options for the computer. We have 3 different options. And so you'll notice that this is clearly the obvious winner, but in the state of Minimax, it goes through the entire tree, which is different from depth first search. It goes through the entire tree until it finds the winning move and the minimize of the maximum possible points it can win. So is there a way we can make this better? Yes, I'm sure you've heard about pruning, where in our human intuition, it makes sense. Well, why don't we just stop when we win? Or when we know that we're going to have a game that allows us to win. And so this idea is the idea of simple pruning. And so when we combine Minimax and simple pruning, we have, anyone know?
Alpha beta.
Yes, our 6034 head TA knows about this. We have alpha beta pruning, where we prune away any branches that cannot influence the final decision. So, in other words, you wouldn't keep exploring the tree if you already knew that a previous turn would allow you to win. And so this idea in alpha beta pruning, we have the alpha and the beta. And so the details aren't important for you to know right now, but the idea is that we stop whenever we know we don't need to go on any further. So in the games of tic-tac-toe and Connect 4 and chess, we have relatively low branching factors. So in the case of tic-tac-toe, we have 2 to the 4th branching factor. But what if we have really large branching factors like AlphaGo? In AlphaGo, we have 2 to the 250. Do you think that Minimax or even alpha beta pruning would be an optimal algorithm for this? And the answer is no. And this leads us to our next section, where Yo is going to talk about how we can use the Monte Carlo tree search algorithm for games with really high branching factors, and using the random expansion to allow us to see ultimately how AlphaGo, which is Google's AI, was able to beat the leading Go player in the world.
Alright guys, so this is the part where we explain the algorithm itself. And before we dive into this, I want to make something really clear, which is that because these are technical details and because we actually want you to understand them, and because I definitely didn't understand this the first 3 times that I read the paper, I really want you to feel free to ask any questions on your mind with the knowledge that, as in my experience, it is very rare that someone asks a question in class that someone else isn't thinking. Okay? So really, whenever you have one. Okay, so why are we doing this? Well, the ideal goal behind MCTS is that we want to selectively build out different parts of the tree. So the depth first search kind of way, the exhaustive sort of search, would have us exploring the entirety of the tree, and that our depth is limited by looking at all the possible nodes at that level. But what we want is because the amount of computation required for that explodes really quickly, with the number of moves that you're basically looking into the future, we want to be able to search selectively in certain parts of the tree. And so, for example, if there are less promising parts over here, then we care less about looking into the future in those areas. But if we have, a certain move in chess, for example, there's a certain move where in 2 moves I'm going to be able to take the opponent's queen, right? Then I really want to search that region and figure out whether that's going to end up being a significantly positive move for me. And so the whole goal of our algorithm is going to be growing this asymmetric tree. How does that sit with people? Okay, great. So, how do we actually do this? We're going to be going over a high-level outline, but before we do that, let's talk about our tree, which you are going to get very familiar with. It's a little bit washed out. Can people see that this is red and this is blue? Okay. So this is our game state when we start our game. It can be a tic-tac-toe board with a few moves placed, a game of chess with the moves configured in a certain way. And so our player, which is the computer, has 3 separate moves that they can take. And so each of those moves are represented by a node. And each of those moves have response moves by the opponent. Okay? So you can imagine that if one of these is a tic-tac-toe board with just a circle, then one of these is with that circle and an X placed right by it. And as you sort of go down this tree, you start understanding that, okay, basically it's the way that humans think about playing these games. If I go here, well then what if they go there, and then what if I go here? You're trying to think through the set of future moves and try and evaluate like whether your move will be good in a long-term sense. Okay, so the way that we are going to expand our tree, as we said, to create an asymmetric tree, is first of all, we're going to descend through the tree. We're going to start at the top, and we're going to basically jump down some sequence of branches until we figure out where we're going to place our new node, which seems like kind of the key operation here, right? To create an asymmetric tree, it's all about how you build an asymmetric tree. And so, for example, in this case, we're going to have picked this sequence of nodes, and once we get to the bottom and find our new location, we're going to create a new node. It's not very hard. Then we're going to simulate a game from this new node. And this is sort of the key part of MCTS, is that once you get to a new location, what you're going to be doing then is you're going to be simulating a game from that new location. And we're going to talk about how you go about simulating a game from this more advanced game state than what we started out from. Does anyone have any questions right now? We will be going in depth into all of these steps, but just in a high level sense.
Just a quick question.
Yeah.
So create the new node, is it probabilistic to create a new node that is most probable to win, or?
No. You're creating some new node. We'll talk about how we pick that new node, but we're just making a new node and we're not talking anything about probability. Okay, the next thing is that we're going to update the tree. So whatever the value of the simulation delta was, was we're going to propagate that up and basically add that to all of the nodes that are the parents of that node in the tree and update some information that those nodes are storing. This is going to be good because it's going to mean that it's a lot like in search algorithms where you have trees, that the entirety of the tree remains up to date with the information from every given simulation. And we're just going to repeat this over and over and over again. And slowly our tree will grow out until whenever we feel like stopping. This is actually one of the nice things about MCTS, is that whenever we decide that we're out of time, like for example, if you're in a competition playing a champion Go player, you can stop the simulation, and then all you have to do is pick between one of the best first moves that you're going to make. Because at the end of the day, after doing all the simulation, we're still right here, right? And we're still only picking between the moves that go from immediately where we start. Yeah.
The first step where you say you descend through the tree, is that dependent on some initial region of interest, or that's kind of arbitrary how you begin to create your tree?
So we'll go through how you pick where to descend right now. But I guess it's any possible move that starts at your starting game state. Does that make sense? Okay, great. So before we move on to the algorithm itself, let's talk about what we store in each one of these nodes. So now we've added these numbers, and what these numbers represent is that nk, as in the value on the right, is the number of games that have been played that involve a certain node. So for example, if I look at this node, that means that 4 games have been played that involve this node. A game that has been played that involves this node just means that one of the states of the board at some point in the game was the state of the board that this represents. And so, for example, if I have a game that was played here, right? If I know that I played this game once, then that guarantees to me that I played this game once because this is a precursor state to this game. Make sense? Yeah.
How can the 2 ends below that node not add up to the value in that node?
Okay. That'll come when we start expanding our game. But that's a great question, and intuitively speaking, it should. Yeah.
So you're saying you're storing data from past games about what we've done before? Okay.
Yeah. And so
past games outside of this current simulation?
No. Past games in this current simulation. Yeah. And then the other value is the number of wins associated with a certain node. And these are going to be wins for player 1, which is red in this case. Okay. It would get confusing if we put both of them, but they're complementary, right? So for example, 3 out of the 4 times that the red player visited this node, they won in that node. Okay. And these are the 2 numbers that we're going to store, and we're going to see why they're significant to store later. All right. So first, descending, the key part of our algorithm that we were talking about. And when descending, there are these 2 sort of counterbalanced desires that we have. The first of them is that we want to, explore really deeply into our tree, right? We want to think about, okay, if they do this, then I'll do this, and then I'll do that, and so on and so forth. And we want to think through a long-term strategy, but at the same time, we don't want to get caught in that. We want to make sure that, we're not missing a really promising other move that we weren't even considering because we were really going down this certain rabbit hole of the move that we had thought about before. This is illustrated by the SMBC. Oh my God. The SMBC comic about academia and how if someone tells you that a lot of really great work has been done in an area, that means nothing about how promising the future work will be. Okay, so it's all about expansion and exploration. And the way that we're going to balance expansion and exploration in order to create our really nice asymmetric tree is the following formula. And it's fine if that looks really confusing and messy, but actually it breaks down quite nicely into two parts. So this formula is known as the UCB. You don't need to know why it's an upper confidence bound. Well, let's just talk about what's inside. So first of all, you have this term on the left. And this term on the left is the expansion term. It's basically proportional to the likelihood, the expected number of times that you're going to win, given that you are in a certain node, and that you are a certain player. And so it's basically the quality of your state in some abstract level. If we knew this perfectly, then we would be doing great, because that's the thing that we're looking for on some grand level, right? The expected likelihood of winning from a certain state. On the other hand, you have this exploration term. And you might not be able to read the font there, but what this is basically saying is that it looks at the number of games that I have been played through, and it looks at the number of games that my parent has been played through, and it tries to preserve those numbers at a certain ratio, like a log ratio. And what that effectively means is that the number of times that I have been if I have been visited relatively few times, and if the denominator is small, whereas my parent has been visited many times, which means that my siblings have gotten much more attention, then the likelihood that I will be visited again actually increases. So this is biased on the one hand towards nodes that are really promising, and on the other hand towards nodes that haven't been explored yet, where there's a gold mine and all you need to do is dig a little bit, potentially. And we don't actually have an analytical expression for this, but we can approximate it. Because you can think that the expected value from a certain node is, roughly speaking, approximately the ratio of wins at that node to the ratio of times that node has been visited at all. Okay, so let's talk about actually applying this statement, right? Because what this statement is going to give you is it's going to give you a value, like some number for here, and some number for here, and some number for here, and so on. So when we start descending through the tree, we're going to start at the top node, and then we're going to look at the 3 children of that node. And we're going to compute this UCB value for each of these children, and pick whichever one is the highest. So just as a thought for a moment, what if we ignored this one, and what if we're just computing the UCB of these 2? Does anyone have any intuition on whether the UCB would be higher for this node or for this node? The left node? Okay, so why is that?
It has a win.
Yeah, it has a win.
They both been visited at the same time.
Exactly. And so clearly the exploration term is going to be the same. Because it's not that one child has been loved less than the other, but the expansion term is going to be different, and so it's definitely going to pick this one. Although in this case, what we're going to say is actually that this is so much more promising than the others, that it's actually going to pick this left node. And so it's going to expand and it's going to look down. And now when it looks down, it's going to compare between these 2. And this time, remember that this is our opponent, right? And so our opponent wants to minimize the number of wins that we have, right? Which means that our opponent is going to want to pick the one that we're less likely to win in, and they're more likely to win in. This is the idea of minimax. I'm minimizing how well my enemy does in this case. Anyway, so now, although again the exploration term might counterbalance it a little bit, right? Because technically this has been explored more, but we're going to pick the one on the left again, and we're going to get to that location that we got to originally. Now, when we're comparing between these two, between a node that has been visited once and a node that has never been visited, can anyone guess which one of these it's going to pick? Yeah.
Never revisited.
Yeah, exactly, because this number is 0. And so if the parent has ever been visited but the node hasn't, this is going to be infinite and it's going to have to pick the node that it has never seen before. Okay, so that's how we descend through the tree. Does anyone have any questions on that? Really, it's totally fine. Like, we're going to be talking about this stuff for a while. Yeah?
The left node that has the 4 for n sub k, wouldn't that be 3 because there's 2 and 1 below?
So no, because of the way that we're going to be updating the tree, which we'll talk about soon. Yeah.
So, I mean, I like the concept, but if it's a deterministic game, why couldn't you build this tree before you start the game?
That's a great question. That's really up to computer memory limits. As I think that Ian mentioned, the number of states in a game of Go, it's a 19 by 19 board, and you can place something in every state. It's something like 2 to the, what? 250. It gets kind of, you could never explore the entire search tree.
Okay, so would you build the first few layers, or I mean, you're going blank? It doesn't make any sense you're trying to do this real time when you could have done something offline.
So it's definitely true that if you know a state that you're going to arrive at ahead of time, then you can totally do that. But in a game that's sort of large enough that, in order to do that for all of the possible states would take that much more time and take that much more memory, it doesn't end up making that much sense. And also something to point out here is that for most of the games that we're talking about, simulating a single run through of a game is really fast. So if you think about it, how long, well, let's actually get to that in the next piece. But the point is that building out this many levels of a tree for a computer takes probably on the order of less than a millisecond, right? And so doing this for a really, really huge tree is also just it's peanuts because they're such simple operations, but it would get expensive when we start building out the tree to like serious depths.
Well, I mean, yeah. But a game like Go, how many nodes would you have?
So on each level, in the beginning, we have something on the order of 400 nodes, and we have a depth of about, I think most games end after 250 steps or something like that.
So like just to build, if you go in there blank without any nodes built, you have to, the computer, like you said, if it hasn't visited a node, it has to go there before it descends further, right?
Yeah.
Basically like breadth first.
So it's sort of like breadth first, but not quite. And there's an important distinction here, which is that it doesn't have to build out this or this node, or any. It doesn't have to build out all of the nodes at a certain level. All it has to do is if it branches down to a certain like subregion, that it can't descend in that subregion below one of its siblings without having at least looked once at all of its siblings. After it looks once, it can do whatever it wants. And the point is that it doesn't mean that the tree has to be kept at an equal level. All it means is that the tree, in order to descend on a specific part of the tree, it has to at least have visited the direct neighbors once before. All right, any more questions on this before? Yeah?
What's the advantage necessarily of having to visit every sibling?
Well, one of them is that the advantage of having to visit every sibling, the way that I think of it, is that you don't want to be missing out on, potentially being interested in some siblings and not others. And it sort of comes back to the exploration versus expectation distinction. That, we do want to descend into the region of the tree that is really valuable to us, but at least having explored a little bit, at least maintaining some baseline, which really isn't that costly compared with the size of the tree, right? 400 moves is not that bad compared with 400 to the 250.
Are these simulations, they're just random simulations?
So we're going to talk about that in a minute. Any more questions before I go on to that? Okay, so next step is expanding. And this is very simple. You just create a node, and you set the two initial values. And the initial values are, the number of times that it's been visited is 0, and the number of times that someone has won from there is 0. Are you good with that? Yeah, that's like the easy part of this algorithm. All right, now simulating. So simulating is really hard. You can imagine that if you get to a certain node and you've never seen that node before and you don't know what to do from this node onward, that, if we knew how the game was going to play out, that is exactly what we're searching for and we would be done. But we don't. And in fact, we have no idea how to go about simulating a realistic game and a game that will tell us something meaningful about the quality of a certain state. And so, as you correctly guessed, We're going to do it randomly. We're just going to pick, we're going to be at a certain state, and then from that state, we're just going to pick random moves for each of the players until the game ends. And if we, as player 1, win, then we're going to add 1. Then we're going to say delta equals +1. And if we don't win, or if we tie or lose, then we're going to call it a 0. You can see in this graph, we're just sort of descending randomly and not thinking about it. And it turns out that this is actually great because it's really, really computationally efficient. If you have a board, even if it has 400 open squares, populating it by like a bunch of random moves doesn't take you very long. It's like on the order of not that many machines there.
So that's why you don't store, if you go down a tree randomly,
yeah,
you already have simulations for nodes when you get to them sometimes. But
this
you
is
don't
actually
store it because it would remove some of the randomness?
So you're totally right, actually, in this case. I've thought through this, and I can't come up with a reason why you wouldn't store the sort of temporary values that you find all the way down the tree, but they don't in most of the literature that I've seen discussed. But you're totally right about that. Does anyone understand that distinction? The fact that we only hold on to the result here and don't theoretically make nodes for every place down in the tree just because we could, just because we've seen them before. We don't, and it doesn't really matter in this case, but it's theoretically a slight speed up that you can do.
But you reduce that quest in general.
Yeah, a little bit. Okay, so we can look at an example of simulating out a random game and get maybe some intuition for why a random game would be correlated with how good your board position is. So for example, here we have a tic-tac-toe game. Circle is going to move next, but as hopefully you can see, because you've played tic-tac-toe before, this is not a particularly promising board for X, because no matter what Circle does, if X is an intelligent player, X can win right now. It has 2 different options for winning. And so if you simulate this forward, randomly, what you'll get is that 2/3 of the time, X will in fact win, even if the players aren't really thinking of it ahead of time. Yeah?
So then why not do N simulations at a node instead of just a single simulation?
Totally can do that. That's in fact something that makes sense to do and that some people do. Although what you'll find somewhat soon is that considering that we're going down the tree and that sometime soon we're going to explore all of its children, there's a good question of why do N simulations now when you could just descend through the tree N times and thereby do N simulations by going through the thing and also building up the children. Okay. Now this case is
This gives more importance to why you do breadth first, because if you're doing random simulations, you would ignore possibly the best one. If your first random simulation here was that O wins, you might ignore this node, which is
right, absolutely.
really bad.
Which is why it matters that we do this so many times that we sort of drown out all of the noise that is associated with playing a game out randomly. And actually, let's talk about that. If there's a lot of distance between where we are right now and our end result, like for example in this game, if I were to tell you how good is this board position, if you are one of those people who's played out every game of tic-tac-toe, you'll know that this is great if you want it to be. Or actually, I don't remember. Does anyone remember? Anyway, the point is that is not easy to do if you are doing random simulations from where you start, right? That the correlation between your current board state and the quality of that state actually sort of drops precipitously. And this, for me, is one of the hardest parts to stomach about Monte Carlo Tree search. Although, as Nick will explain to you, it actually works quite well. And one of the reasons that it works quite well in practice for more complicated applications is that they sort of do away with this assumption of random simulation. Because even though random simulation does allow you to explore all the states, if you have some idea of what a reasonable quality approach would be, then using that, as long as it's not that much more expensive computationally, can help you in your simulation. But right now we're still talking about total randomness. Okay, how are people doing with that idea? All right, great. Now we're going to update the tree with the result of our simulation. So given that we had some result lambda, we're going to propagate up the parents. And for each parent, we're going to add that the game has been played there once, and that the result of that simulation gets added if it was a 1. And so, for example, if there was a win in this game, then this becomes 1-1 because now it's 1 once and it's been visited once, and these two get incremented by 1, and these two get incremented by 1, and that in itself comprises a complete iteration, a complete single iteration of running Monte Carlo tree search, which means that now we can keep doing this over and over again, building out the tree and slowly making it deeper and making it deeper in selective areas, and having these numbers increase and increase, and be more and more proportional to the actual like expected value of the quality of the state. Until, does anyone have any questions about this idea? Okay, so until we terminate, we need to come up with a way of terminating. Now, again, we said we're going to pick what the best child is going to be, right? What the best immediate move from the start state is going to be. And that is what that's the move that we're actually going to play. And so, how do we determine what the best is? Well, the trivial solution is just the highest expected win given k, right? And so what that, in our case, is going to be is, the ratio of number of times that I won from a given early state to the number of times that I visited it. However, this doesn't actually work as well as we might hope. Let's propose the following scenario, which is that you have a tic-tac-toe game like this, and you have been exploring the tree for a while, and you've been really mostly like looking at these two nodes. Now, one of these nodes, if you sort of think it through, this node is quite promising, and you've been exploring it for a while. There is a winning strategy from this node. It's that circle goes here, and then x goes here, and then circle loses because x has 2 options to win. However, it's explored this a bunch of times, and for some reason, due to the randomness, this is at 11 out of 20, whereas this state, which is inherently inferior, is at 3 out of 5 because of a bunch of randomness and because it hasn't been explored as much. And if we had looked at this one as exhaustively as we had at this one, then it probably would, you probably would actually say that this state is better. And so, you can create an alternative criteria, which is that it's the highest expected win value of one of the children, but also that value has to be the node that has been most visited so that they aren't explored by different amounts. What this sacrifices, however, is that this means that we can't terminate on demand. This is not always going to be true, and therefore we're going to have to let the algorithm run until that's true for some start state, which means that maybe it's not a criteria that we want to apply, even though we know that it would be wise to do so. All right, are there any questions about how we pick the terminating node? Okay. So, that was the whole thing. And now we're going to do it lots and lots of times until you guys are sick of Monte Carlo tree search. So, this is our tree. It's more or less what we had before. And the first thing we're going to do is we're going to look at the top, right? And we're going to pick one of these children. Now, let's say that we looked at this, and it turns out the one on the left is really valuable. I think it's the one. No, yeah, never mind. It's wrong. So the one on the left has been explored a whole bunch of times. Remember that it's that this term starts becoming larger for the ones that haven't been visited as much. And so we're going to descend from this one. And now we're going to descend, and we have these two options. Now, given what you know, would you expect that the node that this is going to pick is going to be the one on the right or the one on the left? On the right, because it's never been visited before, and so this term is going to explode. And so we're going to build a node there. And then we're going to simulate a game, and the result is a win, which is bad for this player. That means that they probably didn't want to make that move. And so we're going to propagate that value up, and we're going to start the algorithm again. And it's going to compare between these three, and now it's going to pick the one on the left. That was yeah. And now that it picked the one on the left, it's going to compare between these two states. Now, which of the two is going to have a higher expansion factor?
Don't you invert it though, because this is the opponent?
Exactly, you do. Because 2 out of 3 is actually better, because it's 1 out of 3 for the opponent who's currently making the move. So the one on the left is going to have a higher expansion factor, and the one on the right is going to have a higher exploration factor. Does that make sense for people? It's okay if it doesn't. Okay, so we're actually going to pick the one on the right, because the other one is doing 3, and it has lots of its mother's love, and now someone else needs a turn. And so we're going to expand that node. It doesn't matter, they're both equally likely to be expanded. We're going to simulate forward, and it's going to be 1, which means that was probably a wise counter move. Great, okay, yeah.
So when it's the opponent's turn versus your turn, the exploration factor is the same, but we invert or complement the expansion factor, right?
Yes, so the key here being that this takes in both the state that you're talking about and the player that you're talking about.
But regardless of the player, the exploration factor will always be the same.
Because it's only the number of visits, and it has nothing to do with the results of the simulation. Yeah?
If you wins, and you have the +1, the +1, and you propagate it up. But I'm wondering, I'm not sure, like, so if the opponent wins, do you also, you're like, propagate up and like, yes, increment as well, or do you subtract it, or like, why? Because like, the opponent's winning, wouldn't you want to bet why don't want to go here?
Yeah, so if the opponent wins, then what you do is you propagate up a 0, which means that WK is not incremented, but NK is. As in, so, you know, I think we actually, have we seen a 0 yet? Yeah, there's one soon. But yeah, but the idea is that rather than subtracting or anything, all you do is propagate up the result of the game, which in this case is 0, which means that all of those states seem to become more valuable to the blue and less valuable to the red, because these numbers are lower than the otherwise would be.
Okay.
So yeah, so we propagate this up, and you know, this becomes better. What we've sort of done here is we've figured out a theoretical counter move to blue moving here, right? That's how you should think about this whole tree. It's really a lot like the way that humans think about these things. You know, if I do this, then what if they do this? Well, then I'll do this, and I see that I'm sort of successful when I do that. Okay. So now we're going to look again at the top, and we're going to pick one on the left, because it's really promising. 5 out of 6 is like a good number. And we're going to look at both sides, and which one is blue going to pick now? Well, it's going to pick the one that it's going to be more successful in, which is 2 out of 3. I realize that this is actually not the kind of thing where I can necessarily ask people, because I'm the one who's decided which node it's going to be. But anyway, so then we go down here, and there's an equal likelihood of picking either of those nodes. And so we're going to pick one at random, and so that's going to be the left one. And we're going to create an empty node, and we're going to play it out, and it was a success for blue, which is amazing. Because what this means now is that suddenly, in this tree of, you know, this really good move that red could make that blue wasn't finding any response to, suddenly there's hope. Because we're going to propagate this back, and that means that blue actually has a response move to that sequence of red's moves. And so it's going to propagate up, and this state's going to be more promising for blue and less promising for red. And so that region of the tree that we had dug into is a little less promising. So we're going to look back up, and this time, instead, we're going to evaluate the thing that is both promising from, you know, the expansion factor, and also promising because we haven't looked at it very much, the exploration factor. We're going to pick between these two. Which one is going to be picked here? Because the exploration factor is the same, but the expansion factor is higher for the one on the left. And we're going to look down, and it's going to show us a node. And the result is going to be a win for red, which means that red has found a good counter move to the thing that was previously promising for blue. We're going to propagate that back up. And finally, we're going to pick the one farthest on the right. Because even though it's terrible for red, and even though it's never won when it's tried it, it has to obey this idea of the exploration component to find out whether maybe there isn't something promising in there. So it explores, and it goes down, and it has to pick the one on the right. And so it does. And it plays this game out. And it's a loss. Again, which sort of goes to show you that, you know, blue has found yet another superior move to this really bad move of red. Where probably this move of red, you know, if this is a game of chess, is I like move my queen directly in front of the opponent's row of pawns and I just leave it there, right? And like there's nothing good that's ever going to come of it, but we have to explore it just to find out whether, you know, there isn't some magical way that actually works out for you. And as you can see, we've built out this tree over and over and over again, and it's starting to look asymmetric. And we're starting to see that there's really this disparity between, you know, exploring the regions that are promising in this tree and exploring the regions that are not, and that don't really matter to us very much. And that this is exactly what we wanted from Monte Carlo Tree Search. That was like why we started the whole endeavor in the first place. All right. The next thing I'm going to talk about is pros and cons. But before I do that, does anyone have any more questions about the algorithm? Yeah.
So it's still not clear how we're getting nodes with different denominators than the geometry.
Okay, so the reason for that is that because of the way that we're simulating it through, we're not holding on to the results of the simulation as we're going farther down the tree than the lowest node that we've expanded. And so, for example, when you simulate from here, you're going to, you know, propagate that value here and so on. But then when we expand below, even if in the course of this guy's simulation, it happened to go through one of the states that we expand to below, it will not have incremented the value for that state because we weren't keeping track of it yet. And so theoretically, if we were keeping track of all of the simulations that we have in fact run, the numbers beneath these things would be higher. You
you've already run a simulation from that. Like, you already run a simulation from that red node when you first built it, and then when you created those two ones, each of those have simulations. So you have a total of 3
Okay,
from
I
that.
see.
So would the denominator always be one more than the sum of the children? For like,
Yeah, in the
is that-
implementation.
Okay.
Yeah.
So when you're, yeah, I understand how you built that, but how can you, is there like a rule of thumb, like it's time to choose a move, and it seems like you have very low numbers here to make a choice. Is there a rule of thumb on, given games, like if it's 2 to the 4th or 2 to the 250th, whatever, what kind of numbers do you need in that first row before you be confident in C?
So what we'll get to soon is that there isn't, and that's one of the problems with MCTS. But that in terms of which of the moves you will choose, there are actually variants of MCTS that suggest that you more selectively aim towards certain children based on something more than just this sort of blind look right now. In terms of like, if I'm here and it's, creating my next children is equivalent, then there are some intelligent guesses that you can make in terms of which one you should explore first. But although it doesn't particularly matter.
Yeah, I'm just saying, like, computational time being what it is, you might say, okay, if this is the timeline of this game, I can expect to do 1 million simulations, which will give me, if there's 400 nodes, I'm going to have so much in each node.
Yeah.
And is that enough time to say that I can play through a game? I couldn't play through a game with 400 options if I've got like 5 out of 7 or 3 out of 4. That's
Absolutely. And I would say that that's, so far as I know, that's something that's basically verified experimentally. They don't have good bounds on it.
Yeah, test it out.
Yeah. So let's get to the pros and cons, because that is particularly relevant. So why should you use this algorithm? Even though, we've seen tremendous breakthroughs in this algorithm, and, you're going to have to ignore everything that I tell you and remember that this does actually work quite well in certain scenarios. Should we use it or not? Okay, so first of all, the pros are that it actually does the thing that we want it to do. It grows the tree asymmetrically. It means that we do not have to explore, and that it doesn't explode exponentially with the number of the number of moves that we're looking into the future, and that it selectively grows the tree towards the areas that are most promising. Okay, the other huge benefit, if you'll notice from what we've just talked through, is that it never relies on anything other than the strict rules of the game. What that means is that the only way that the game is factored in is that the game is what tells us what the next moves we can make from a given state are, and whether a given state is like a victory or a defeat. And that's kind of amazing, because we had no external heuristic information about this game, which means that if I took a completely new game that someone had just invented for me, and I plugged MCTS into it, MCTS would be a slightly or somewhat competitive player for this game, which is a powerful idea. It leads to our next two pros. The first of which is that it's very easy to adapt to new games that it hasn't seen before, or even that people haven't seen before. And the other, and I mean this is clearly valuable, but the other nice thing about it is that even though heuristics are not required to make MCTS work, and it can work blind, there are a number of nice places in the algorithm that you can actually incorporate heuristics into. Nick is going to talk about how AlphaGo uses this very heavily. AlphaGo is not vanilla Go. It has a lot of external information that's built into the way that it works. But MCTS as a framework, you can imagine, there's your heuristics you can apply in the simulation. There are heuristics you can apply in the UCB in the way that we choose the next node. There are places that it can fit in, and that this serves as a nice infrastructure to do so. All right. The other benefit is that it's an on-demand algorithm, which is particularly valuable when you're under some sort of time crunch, or when you're competing against someone in some competition, or when something is about to explode and you have to make a decision on which reactor to shut down. And lastly, or not lastly actually, it's complete, which is really nice because you know that if you run this game for long enough, it's going to start looking a lot like a BFS tree. Or actually no, it's going to start looking like an alpha beta tree, I think, is what it converges to. Which means that it's a nice property to have. Although this property that does slightly get compromised if you remove the randomness idea, and if you only simulate using specific. Okay. Oh yeah.
Well, so you made an interesting comment when you said, oh, it looks like an alpha beta tree. So it would look like a Minimax tree, right? But have they also incorporated notions of pruning into MCTS, which would make it look like an alpha beta tree?
So, sorry, you're completely right that it does look like a Minimax tree. I think I've seen variants where they do employ pruning, but I haven't looked at them very much. But yeah, I would imagine that they would converge to whatever pruning sort of tree that he's not.
But people have explored incorporating pruning into MCTS.
I think so. I can't cite the examples. Okay, and then lastly, it's really parallelizable. If you'll notice, none of the regions of this tree, other than the original choice, ever have to interact with each other. So if you have like 200 processors, and you decide, okay, I'm going to break up this tree in the first like 200 decisions, and then have each one of those flesh out one of those decisions, that actually means that they can all combine their information right at the end and make a decision for them, which is a really nice powerful principle, as you'll see later in the AlphaGo. Okay, it does have its fair share of problems. The first problem being that it does sort of break down under extreme tree depth, and one of the main reason for this being that that as you increase more moves between you and the end of the game, you're increasing the probability that, or you're decreasing the correlation between your game state and whether a random playout would suggest that you're in a good position or a bad position. The same sort of goes for branching factors. One of the things that people sometimes talk about is that MCTS AIs cannot play first-person shooters because the distance between the number of things that you can do at every given moment and what would be a successful approach, in the long term after making many moves that each have many branching factors, is that it never even begins to explore the size of the search tree. It's not for the most part, it's not really coming up with a long-term policy, right? It's really thinking about what are the sort of next sequence of moves that I should do. Okay. Another problem is that it requires simulation to be very easy and very repeatable. So for example, if we wanted to tell our AI to, how do I take over Ontario, right? There's not a particularly good way that you can simulate taking over Ontario. If you do it once, or if you try it once, you're not going to have an opportunity to try it again, at least with the same, set of configurations. And actually, one of the things that we really took advantage of is that random simulation happens really quickly, on the order of microseconds. And on the other hand, it does require, the bigger your computational resources that you have access to, the better the algorithm works. That means that I can't run it off my MacBook particularly well for large games. It relies on this, tenuous assumption of random play being weakly correlated with the quality of our game state. And this is one of the first assumptions that's going to be thrown out the window for a lot of the more advanced MCTS approaches, which are going to have, more intelligent playouts, but those are going to lose some of the generality that we had before. Another sort of something that goes off of that is that MCTS is a framework, but in order to actually make it effective for a lot of games, it does require a lot of, tuning in the sense that there are a whole bunch of variants and that you need to be able to implement whatever flavor is best suited for you. Which means that it's not quite as nice and black boxy as we would want it to be as far as, give it the rules and have it magically come up with a strategy goes. And then lastly, as you mentioned, there is not a great amount of literature right now about the properties of MCTS and its convergence, and what the actual proportion of time to quality of solution is. This is sort of true of all modern cutting-edge machine learning things, right? Is that there's certainly a lot more work that could be done, but right now that's sort of a gap in terms of using this for something that's supposed to be reliable. Okay, anyone have any questions on the pros and cons? All right, before we dive into applications, let's talk through a few examples of what games could be solved and could not be solved by MCTS. So, do you guys think that checkers is a game that could be solved by MCTS?
Yeah.
Okay, it's completely deterministic, it's two-player, it satisfies all of the criteria that we've laid out before. Checkers is definitely a game that can and has been solved by MCTS, although not solved to the extent of it can defeat the thing that actually has the solution to checkers. Okay, how about Settlers of Catan? This one's a little bit trickier. Do you guys think that MCTS is likely to be able to play Settlers of Catan? If not, let's throw out reasons why or why not it would be able to. Yeah?
No, because there's randomness.
So yes, that is absolutely the criticism, and that's why we can't apply it vanilla. I sort of put this on here as a trick question though, because it turns out that the MCTS is robust to randomness. That you can actually play, and I realize that's just mean of me to do. You can actually play through games, and if you think about the simulation is actually applicable even if the game is non-deterministic, because it does give you a sense of the quality of your position. And the MCTS-based AI to play Settlers is, I think it's 49% competitive with the best AI to play Settlers of Catan that is not MCTS-based. So it does sort of work. All right, let's talk about the War Operations Plan Response. Who here has seen the movie War Games? Okay, well, it should be more of you. But the idea of war games is that one of the core characters in this world is this computer that has been put in charge of like the United States national defense strategy with respect to Russia, and that it needs to think through possible future scenarios and decide whether it's going to launch the nukes or not. And so, do you think that that Whopper can be MCTS based? No.
Well, it could. It just wouldn't be very good.
Absolutely. Once you fire the nukes, you're not going to get another chance. And so you can't particularly simulate through what the possible scenarios are going to be like. Yeah.
So what if you had, I agree you can't like simulate it in the real world, but what if you had, suppose, a really good model, and you just simulate it based on that model?
So in that case, it probably depends on the quality of your model. If you have a good model for how World War III is going to play out, good on you.
Well, but it is the case that the military does have simulators and they do war games in simulation, right?
Yeah, so yes, that's true. They could certainly try and run MCTS if they want.
And that's what happened in the movie. They were just trying to find the best strategy.
Yes, right. I mean, there you're putting your money in the simulation, not in the.
It's like having MCTS trying to play like SOCOM or something like that.
Yeah, it's definitely about putting money into the simulation and getting really good simulation. If you have a really good simulation, then you can exactly play Whopper. All right. Yeah.
Sorry, back to Settlers for a second. I'm curious if there's like a way to encode the whole like player trading resources thing, or like would it have to be only purely like like using like the importance of traders?
That's a good question. I haven't looked closely at whether they do that or not. I would imagine that they, if it's playing a 2-player game, then I would imagine that they wouldn't, right? Because you don't really trade in a 2-player game. But if they weren't, I bet that you can incorporate it a little bit.
Why do you keep saying? Is it limited to 2-player games?
No, not at all. In fact, there are lots of approaches that do only 1-player games, where you just think of what's the best move that you can make.
Well, no, but I mean, couldn't MCTS handle 3 or 4-player games?
Yeah, it absolutely could. I'm not sure how they computed their head-to-head. Yeah, that might be a completely flawed criticism. I'm not actually sure how the Settlers runs. Okay. Yeah.
A quick question. So let's for instance, if I reduce the chessboard, to only like a 4x4 or 5x5, and run the MCS versus the traditional algorithm like the alpha in the tree, do you think MCS will perform inferior in terms of performance because of this computational requirement?
So the thing about the way that Deep Blue is implemented, which is the AI that ended up being Kasparov and a bunch of these chess grandmasters, is that it has a tremendous amount of heuristic information. There's a lot of external stuff that's incorporated into the system that makes it able to explore the best paths. And so what I would say is that like knowledgeless MCTS based on randomness would take a very long computational time to even become competitive with those kinds of algorithms, and probably like feasibly never would. But if you incorporate heuristic information, I think that there's a bunch of hope in terms of getting MCTS to start performing better. And you can look at what Nick is going to talk about AlphaGo to take some inspiration for how one would go about incorporating these ideas.
So only like suggest we use this algorithm and solve a very big complicated problem, right?
It definitely seems like if you have a really good heuristic model for how like what good states in the game are, that there are that like if it's a smaller search space, that some other models could perform better. Although I'm probably going to eat my foot because this is going to be on OCW and someone's going to come out, like a master chess playing algorithm sometimes. Eat my shoe, not my foot. Anyway, and so one last game. Does anyone know what this game is?
Total War?
Yes, nice. This is Rome Total War 2. It's a simulator for this tremendous real-time strategy game where you play, I think, the Roman Empire, and you're controlling armies and huge infrastructure systems that move and conquer like states and continents and meet in the field and manage resources and do all of these incredible diplomacy feats. And so, do you think that this game could be solved by MCTS?
Yes.
Well, I'm supposed to say no, but I guess that I put it on here, so that's good on you. The way that the AI in Rome Total War 2 is built is that it's built on an MCTS structure. And it in fact does do resource allocation and like a lot of its political maneuvers based on Monte Carlo Tree search moves. There are a bunch of reasons that they explain in the game for why they do this, or in papers released about the game. But one of the nice ones is that it's random, which means that you're never going to play against the same kind of AI twice, because every time the set of decisions that it's going to think about is completely different.
Good question.
Yeah.
So if I want to model any game to the MCTS, does it have to be that the actions I play in a game has to be able to discretize,
Yes. So far as I know, I haven't seen many continuous variants of MCTS.
Okay.
And so I think that it is about choosing discrete actions, which on its most narrow level it does actually break down to here. I think that one of the reasons that this is nice is that there are so many different decisions that could be made that MCTS is really the only approach that can even begin to handle the massive branching factor that's associated with a game of directed report. Yeah?
This also has a consequence of the shittier the computer you play on, the easier the game becomes.
That's interesting. That's probably totally it. That's cool. Okay, so that's everything about how the algorithm actually works. Now let's pass it. I'm going to pass it up to Nick, and he's going to talk to us about some actual implementations for this game, which are pretty cool.
All right. So as Yo said, I'm going to start diving into some applications here, and not only applications, but also some modifications or augmentations of MCTS. It should hopefully clarify some of the side questions you all have been having on slight tweaks to MCTS. And with that, let's get started. Oh wait for it. Now let's get started. So, part 3 application. First thing we're going to look at is an MCTS-based Mario controller. And Mario might seem like some weird thing to test AI on, but there actually is a Super Mario Bros. AI benchmark, which is used to test a lot of AI on how well they can play this platform game. And in case any of you don't know what Super Mario Bros. Is, this is a screenshot. Basically, you control this one character. It's a single-player game, and you can do the ultimate goal is to reach this flag at the end. But along the way, there's enemies. There's some bonus shrooms you can get. If you break open some boxes, you might get coins, things like that. But first, let's just highlight some of the modifications that need to be made, or some of the differences between vanilla MCTS and an MCTS that's going to be able to work for Mario. First thing is that it's single player. The second is we use a slightly different simulation strategy than the initial just vanilla simulation, and someone actually hinted at doing more than one simulation. I think it was you. You're like, why can't we just do N simulations? I think, yeah, so we'll touch on that. Then this also introduces what I would consider to be domain knowledge. And then finally, there's a 50 to 40 millisecond computation time, and that has to do with the frames per second of the game. So you would think that Mario is a continuous game, but if we discretize time into these chunks, then we can use MCTS. All right. Now let's just think about how we could possibly formulate this problem. Can anyone think of what each of these nodes would be if we're playing Super Mario?
Jump.
Sorry.
Jump would be like the first node, you're going to jump.
Okay, that might be a way to formulate it, but I think that could get...
Oh, it's not your controller inputs for each of those nodes?
Right, so the node itself is going to be an action.
Individual frames?
Yeah, basically. So it's going to be the state of a game, what we'll call a state. So it's basically just a screen grab, and it takes it, in this case, it's a 15 by 19 grid screen grab of the game, and it'll have information about, it knows Mario's position, it knows the enemy's position of the blocks, etc. And then, as Yo was saying, in MCTS, we have values associated with our nodes, and so it'll also have a value, but we'll get into the value in the next slide because I can't really fit it all in here. But then with that being said, for our node, that being the state of the game, what would make sense for the edge? So how do we transition from one state to another state?
Jump.
Yeah, exactly. So this is where the jump and all that comes into play. So the actions that you can take, I didn't list all the actions, you could also have like jump left, jump right, all those things. But basically the actions are what take you from state to state. So I just drew out what a node might look like if you use the jump action. You might have Mario up in the sky. All right, other questions?
Does it just run the rest of it? Like, because that little thing's moving, right? The thing at the bottom?
Well, I mean, it's not moving in this moment in time. Like, we're discretizing time right now.
Yeah, but I'm saying, like, if your action is jump, you would get, you know, you
Right.
would have 1,000 nodes, because if you didn't plan out where that thing's moving left or right, then it would be.
Yeah, right. So in each state, we have the enemy position, and we know the speed and direction. And so we know when we go from this node to one time step later, we'll know where the enemy's going. Yeah. Any other questions? All right, moving on. Oh, sorry. Let me just preface this part real quick. So in our other simulations, at the end of the simulation, we would get either a 1 or a 0. If we won tic-tac-toe or we lost tic-tac-toe, right? But that won't really work too well here because there's a lot of other factors that go into play when you're playing Mario. And also, if you're doing a simulation, more than likely, you're going to end up hitting an enemy and dying, or falling into a gap and dying. So a lot of these simulations might all return 0, and in that case, you can't really distinguish between them. So this is why I say this version of MCTS introduces what I would consider to be domain knowledge. Basically, they're assigning scores to potential things that could happen along the way. And this is basically telling the AI that collecting a flower is a little bit better than collecting a mushroom. It's telling it that getting hurt is bad right off the bat. All these things into the score are giving the AI some sort of domain knowledge about Super Mario Bros. That is helping it calculate the simulation results. And as it says here, it's just doing a multi-objective weighted sum of all these things. So throughout the simulation, it's just adding up your score, and then that's the score that is going to be propagated. Other questions about the score? Yeah.
You said that it adds up all these values and it propagates it upwards. Is it possible to just propagate the multi-part sum as opposed to the individual factors as opposed to propagating one value that you create? Like, are you essentially propagating all, what is this, 15 values upwards at every node, or are you propagating one value?
Well, one value. It's the
that you make by like adding together
Right.
each of them with some factor. Okay.
Yeah. All right. And also, just one thing to note here is distance. You get 0.1, and these are all parameters that have been tuned. So in the initial version, distance was, I think, a reward of like 5, but probably realized that that made Mario skip past a lot of coins and things, and so he tweaked the score for that. And also time left is 2, so there's some weight there. You want to get to the very end of the game. Yeah.
If you're pushing up this like score, it's no longer like a win over loss. It's not W over N. Is it? What is it exactly?
You can just use the score.
The score is
Basically,
the.
Yeah. So in MCTS, you have this idea of like what you're propagating is like your Q value, and so you could have that be 0 or 1, but
It's like the sum of all the scores in the nodes below over the number of games you played.
So basically, what you would be getting when you divide by the number of simulations is like your average score at that node.
You have like kills by fire and stomp and stuff like that. If you have a positive value, isn't that kind of seem like it's good to be killed by fire and stuff like that?
Oh, this is killing an enemy by fire. Like Mario, if you collect a certain flower or mushroom, I think flower, then you have like fire breath, and you can,
So Mario's status is Mario dying? Is that what that is?
No, Mario's status is like, I believe Mario's status is the fact that you can upgrade Mario by collecting things like a mushroom, you become like a Fire Mario, or whatever. So that gives you a lot of points, because if you become a Fire Mario, then you're like you're more likely to not die by running into enemies, because you have fire spewing.
You said they spend a lot of time tuning these parameters, sort of. Isn't it generally, though, just an optimization framework, and that's like some formula? So they tune the parameters just to make it behave in a way that we think is nice. But if you change the values, like it'll do the right thing for that equation.
Yeah.
Okay.
Yeah. They were tuning this to make it play how they wanted it.
Okay.
Yeah.
Is there any reason these values can't just be a reflection of the point values they actually give you in the game?
I mean, that's a strategy you could use. I don't see why not. Yeah. That might affect certain things. I mean, obviously you can change these to whatever you want. It'll slightly tweak which simulations are scored to be better, which will in turn change which nodes you end up choosing, which actions you choose. But yeah. All right, so we'll move on. So the next, so we know about scoring simulations. Now we're going to look at exactly the simulation type that's used to play this MCTS controller. So the regular version that Yo talked about is just choosing a random node at each level in your simulation. But there are some other strategies, and someone brought one up. But first, let's look at best of n. So in this one, you choose 3 random nodes at each level, except you stick with the best of those three. So choose 3 random nodes, you stick with this one, go to the next one, you would choose 3, like any random 3, take the best one, and then go to the next level. And you're able to do that with this game because because of the way the scoring works, you don't have to get to the end of the game for your score. You actually could collect a coin along the way. So like, if this is like jump and it gets me a coin versus moving left and right that don't give me any points, then this is the node that would give me the highest score, so I would choose that one, etc. And then the final one, which is the one that's actually used for this controller, is multi-simulation. And this was brought up by him, don't know your name, sorry. But basically you run multiple random simulations from your node, and then you propagate up whichever of those simulations gave you the highest value. And the reason to do multiple simulations is to attempt to increase the accuracy of your simulations. So if you just do one simulation, you might just get really unlucky, but if you do 3, then you can take the highest value and use that as your value. And then since the whole point of this is to try to make moves that get you the highest values, then that'll make your random simulation value more accurate. Questions about multi-simulation?
So when you do the multi-simulations, how do you choose like how many simulations you do versus the time of finish?
So there's a trade-off here. So the more simulations you do, the more accurate your simulation, the more representative your simulation will be of the actual game. Like, you could technically do you could run like 2 to the whatever simulations to try to get every single possible action, and then take the max of that, and that would give you the maximum value. Like, that would be ideal, but obviously that takes more time, so there's a trade-off between computation time and the number of simulations you run. And that's just something that they probably just played around with.
Do you use some time resource allocation to determine the number of simulation you do, or something like that? Like for instance, you have to finish the decision within 5 minutes or 10 minutes when you play chess, right?
Yeah, so in this competition, there's different computation time budgets that you get. And I believe the reason for the different computation time budgets is the frame per second of the game. Yeah. Oh, okay, so I told you all about how this is set up. We went over the scoring, the nodes, what the edges are, what the simulation strategy is used. And so you probably want to see it in action. So this is always a risky move, trying to get a video to play.
It's actually in the background.
Oh.
Hit escape.
Okay, got it.
And now I guess we
can drag it over, I guess. Yes. How do I make this full screen?
Hit the
Alright, we can just watch it from here. Alright, so here's this MCTS-based Mario playing controller. You can see he's actually wrecking, he's doing some serious damage here. But those lines that you see, the reason they're different colors, it's not showing like different players or anything like that. It's just using different colors so you can see the different layers of his tree search. And so you can see he actually went backwards there, and that's because in his simulation, one of the backwards ones landed on an enemy, and that gets 2 points from our scoring system, versus if he had just gone forward, he would have gotten some distance points, but not. Also, he has just tons of enemies. So his simulation is quickly being able to figure out that he can jump on all these enemies, so he's just wrecking all these guys, getting lots of points here, collecting the coin, etc. You get the idea. It's pretty awesome to watch. Oh, there's that flower we were talking about. So now he's actually a fire-spewing Mario demon, and he's doing some serious damage with that. Stepping on the missiles. I didn't even know you could step on the missiles. All right. We could watch this for a while, but we'll exit now. So it looks super promising in this video. I don't know how to close Mac stuff.
Just click on the background.
There it is. Okay. So the demo looks really cool, looks really promising. But let's take a look at the charts here. We all want some quantitative stuff. This is the chart. The score is on the y-axis. The bottom is computation budget, which is something that you were talking about. And I just want to highlight, to make this a little more visually appealing here, all of these things that I highlighted are using this, it's labeled as UCT, that's upper confidence bound tree. Remember Yo talked about upper confidence bounds? That's just essentially what's used in MCTS for guiding your tree search. So these are all the methods, but then UCT multi, which is this purple square, that's saying it's using MCTS, but it's doing the multiple simulations. And you can see this multi plus care is also in the top. So both these use the multiple simulation technique, and then the plus car is actually, they added an extra scoring mechanism for carries. I believe that's probably like carrying a shell, and that actually made it do better. Then these ones that aren't highlighted are using plain A star and then a refined version of A star. So with increasing time, they do increase score, but they're even worse than just your UCT with just random simulation, no multi-simulations. I guess we're kind of running low on time, which is not ideal. But another thing I want to point out is down at the bottom here, these are the multi-simulations. They actually, they have the lowest maximal search depth, which at first would seem like, what? Like, I have the lowest search depth, but my score is the most. But that comes into play with what you were saying about the trade-off between the simulations and the amount of time it takes. So because I'm doing multiple simulations, I'm taking more time at each node, but that's giving me a more accurate value assessment. And so that lets me choose my action more carefully or with more information. And so that's what's able to give me this better score. Okay, that's all of Mario, so we're gonna move on to AlphaGo. I guess are there questions about Mario before I go to AlphaGo? Yeah.
What's the table going in first?
Yeah, that's a good question. I have a feeling it's because if you're doing best of n, that's really heavily relying on your scoring metrics. And so if, let's say at one step I collect a coin, like if I jump and collect a coin versus if I go left or right, like I'll get more points if I get that coin, but maybe like a missile is gonna hit me in the face if I do that. Right. So it gets rid of some of the, it's kind of like forcing you to do certain moves. Yeah.
Is the A-star heuristic it's using the same value, like it's the same value that you're getting by your simulation?
Yeah, so I'm not exactly sure what the A-star heuristic is. The whole reason that A-star is difficult is because coming up with a heuristic for these types of games is hard. Yeah, but this is not his version of A-star. I believe this is the A-star that was used by, I forget the name of the guy, but it won the AI competition like a couple of years ago. Okay, but I'm going to try to move on to AlphaGo. Does someone have how many minutes I have left?
4.
Okay, we're going to power through. So here's AlphaGo. Hopefully you all know the rules. Just in case, I'll just go through real quick. 19 by 19, you alternate black stones, white stones. You collect enemy stones by completely surrounding them. You can surround a single stone, groups of stones, and your score is your territory plus the number of captured pieces. So your territory is just the area that you're surrounding, and then you just add the stones you've collected. The main emphasis here, the rules aren't super important. The main emphasis is there's very few rules, so you would think it's really simple, but the complexity of the game is quite extreme. At each level, at each turn, you have about 250 options that you can play. Each Go game lasts about 150 turns, so that gives you a total of 10 to the 761 games approximately. And to put that in comparison, here's chess. You can read those numbers. Chess is also pretty complex, but there's 35 options per turn. Deep Blue, it would actually, I think you were talking about building out the whole tree. So Deep Blue would build out the tree for 6 levels and then use this hardcore chess master inputted like heuristic evaluation that it used to find the best move. Except with Go, you have 250 options, which already is adding a lot more complexity. And so that strategy won't work quite as nicely. So what do? We use a modified version of MCTS. Well, it's not what we do. That's what Google's DeepMind team did with AlphaGo. They combined neural networks with MCTS. Coincidentally, we learned about neural networks last class. Probably not a coincidence, but
it's not a coincidence.
There were 2 policy networks in AlphaGo and 1 value network. And another big coincidence here, the 2 policy networks are actually CNNs, which we learned specifically about last class, convolutional neural nets. And the reason for that is the input to the policy neural networks is an image of the game. And remember, convolutional neural nets work really well with images. And so what it outputs, though, is a probability distribution over the legal moves. And the idea is that if a move has a higher probability, it'll be a more promising move for you to take. But another key point is that it's not deterministic. It's not telling you to take this move. It's just assigning a higher probability to this move. And this network was generated by doing supervised learning on 30 million positions from human expert games. apparently there's a giant database of Go expert games, so that came in handy. And there were two different networks training. One of them was a slow policy, the other was a fast policy. The slow was able to predict an expert move with 57% accuracy, which to me was mind-blowing. Like, using this neural network, 57% of the time it could pin where the expert would place his move. But that took 3,000 microseconds versus the fast policy, which suffers a bit in the accuracy, but it's 1,500 times faster. And we'll see where they use each of these different policies later on. But yeah, it can predict the expert move with 57% accuracy. The AlphaGo team is like, that's not our goal. We don't want to predict an expert move. We want to predict a winning move. And so to do that, they took their policy network and then they would use reinforcement learning. So that's where you play the network against like iterations of itself in order to hone in a better policy that's geared towards winning moves. And then they tested this against Pachi, which uses, for the camera, I have no idea if that's how you pronounce Pachi. It might be Patchy, I'm not sure. But there's 100,000 MCTS simulations at each turn. So this is purely MCTS, okay? If it's playing just the AlphaGo policy network, the policy network won 85% of the games. So without any sort of tree search or anything involved, it won 85%, which is pretty great. And that suggests that maybe intuition wins over long reflections in Go. And interestingly, if you talk to expert Go players and you ask them why they did a certain move, they'll just say like, it felt good, or I had a hunch for this. And so that's kind of indicative there. Hopefully not going over time, sorry. But those are the two policy networks. There's also a value network. What the value network does is it takes in a board and it'll give you a value, like how good is this board? A win, like it'll give you a win probability number. So it's 77%, it would say. Like 77% of the time you should win from this board. And so that's similar to the evaluation function of Deep Blue, but rather than a Go master coming in and telling you like, well, if these are connected in this way, and like down here we have this certain thing, then here's the sort of score we should expect. Like in chess, they have chess masters, like if the knight is here and the queen is here, all these specific things. This was actually learned from the reinforcement learning that was happening when the policy networks were playing each other. The value network was learning about those positions during that time. And the predictions get better towards the end of the game, which I think Yo mentioned in his talking. All right, so how do we combine all these into MCTS? Well, the slow policy network, remember, is slower but should give us stronger moves, is used to guide our tree search in order to help us decide which node to expand next. When we expand that node to get the value of the state is the simulation, like before, like normal MCTS, except it's not a completely random simulation. We use our fast policy network to give us a more educated simulation here, but we're using the fast one obviously to save some computation time. So it's giving us probably a more indicative random simulation of what's going to actually happen. And then we also combine that with our value network output. So we run our value network on this node as well, and we add that to our simulation value and propagate it. Interestingly, the AlphaGo team tested out just using the fast policy simulation value and scrapping the value network. And they also just used the value network and scrapped the simulation value. And those both performed worse than if they had these. And another added interesting point here is that these two factors in our value have about the same weight. They were both about equally important. And I think I'll get into that later. But first...
Can I just ask a quick question?
Yeah.
I know you don't want, but so when you said the policy network is used, is that used when you're navigating to the tree to get to a leaf, or is the policy network being used to do the simulation once you're at the leaf, or both?
So the fast policy, so the slow policy is done for this part. Then the fast policy is used for the simulation, because the slow policy does take 1,500 times faster than, or the slow takes 1,500 times longer than the fast policy. You don't want to use that in your simulation because that would just take way too long. So it's basically just a way of making it so our simulation isn't completely random. It has some sort of educated moves. All right. So why use policy and value networks in our tree? Why can't we just use the policy network? Why can't we just use the value network? Well, if we had the value network alone, well, actually, I guess here's a side point. Remember, the value network learned from the policy network, and then also later on, the policy network is improved by our values. And so they kind of work hand in hand. But if we had the value network alone, when we're deciding on the next move, we would have to evaluate every single move, which would take forever. And so what the policy network does is basically predicts the best move with this probability distribution, and it narrows our search space. And then if we had the policy network alone, we'd be unable to compare nodes in different parts of our tree, right? So the policy network is able to tell us a distribution over which move we should take from a certain node, but then if I ask it if I'm in a better position here than in some other place, it won't know. And that's where the value network comes in, because it gives us a estimated number of a value assignment, of an evaluation of that node. And then these values are later used to direct our tree searches based on updating the policy once it realizes, oh, like, I thought this would be a good path, but the value is this, so update, all that. Then why do we combine neural networks with MCTS? Remember, the policy network alone played against Pachi, which was purely MCTS, and it did pretty well, right? So how does MCTS improve our policy network? Well, remember, MCTS did win 15% of those games, so already that makes you think there's something there that maybe the policy network is missing. Also, the policy network is just a prediction, so by using this tree structure, we're able to use these Monte Carlo rollouts to adjust our policy to move towards nodes that are actually evaluated to be good. And then how do neural networks improve MCTS? This point should probably be clear by now. We're able to more intelligently lead our tree exploration. Our simulations are more reflective of actual games, and the value network and the value network and our simulation value are complementary, which I mentioned before. Oh, and just to sort of highlight that, basically the value network is going to give us a value that is reflective of as if we played the slow policy the whole time, and the simulation is if we use the faster policy. So they kind of are complementary. And I know I'm over time, so just want to skim through the stats real quick. AlphaGo, or distributed AlphaGo, won 77% of the games against regular AlphaGo. So it's the only thing that beat regular AlphaGo. And then distributed AlphaGo won 100% of the games against all these. So in a rematch against Pachi, now that we've added MCTS to our policy network and we have our value network, we slaughtered Pachi 100%. Then we decided to see how we'd fare against humans, and by we, I mean not me, I mean Google. And they won 4-1, and Lee Sedol's rating was 3,520, and so now AlphaGo's rating is estimated to be about 3,586. So like, woo, we beat the best dude, except we didn't, because there's another dude who has an even higher score apparently, 3,621, and I think this should be the last part. Here's just a timeline. Basically, tic-tac-toe, checkers were conquered in 50, so like about 40 years later, we conquered checkers. Chess, then we scroll down to 2015, is when AlphaGo was able to beat Fan Hui, who was a 2-dan player, which is considered lower down in the tier of professional Go, but then Lee Sedol was 9-dan, which is the highest, and who was able to beat him like literally last month. And
so good job.
We're done.